All right, yeah, thanks for inviting me. This is a great event. I'm here to talk about JAX. I think in the metaphor of today, JAX is cheap turpentine. But more literally, JAX is a numerical computing library for high-performance, large-scale machine learning. Here's JAX in one slide. It's a very short talk, so I had to fit it all in one slide. JAX is a library that you import, you write Python, NumPy programs, and you transform them with things like automatic differentiation, automatic batching, this sort of thing. And what's special about JAX is it's sort of been built from day one around this large-scale machine learning compiler, which means you can run all this code on accelerators, on supercomputers, like TPUs, but also GPUs, even like Amazon Trainium. So that's JAX in a slide. Why is JAX interesting? So JAX is the system that powers all kinds of large-scale machine learning at Google, like Gemini, but also things like VO and Genie and our robotics research. It also powers things outside of Google. So Anthropic is a huge JAX user on TPUs. XAI uses JAX for its large-scale pre-training on GPUs, and Apple uses JAX on GPUs and TPUs and even Trainium, apparently. So JAX is also used outside of industry and like academia. There's this really exciting project from Stanford on like a totally open research platform for language modeling. Super awesome. Check it out. JAX is also used for things that you don't usually think of as generative AI, maybe like AlphaFold, things like plasma simulators to try to solve fusion. It's used for things like climate modeling. So why do these places use JAX? Why do these sort of like cutting edge companies and projects use JAX? It's because JAX gives you AGI. And by that I mean awesome scalability, great expressiveness, and incremental composable control. I think this is what people mean when they're talking about AGI. And the way it does that is by working closely with this like large scale compiler, XLA. So I want to say a little bit more about this incremental composable control thing that we work on. So the idea is that sometimes you want, you're in research mode and you just want to write down the math of your machine learning model. And that's sort of like all the way on the left of this figure. You're just writing math and you're leaving it to the compiler to figure out how exactly to execute this thing, maybe how to scale it up. But actually these days, oftentimes we're doing a bit more to squeeze the performance out of our large-scale systems, or even all the flops out of our chip. And this is where we want to sort of take more direct control of the machine, be a bit more imperative, and tell the machine exactly how to do this computation. And when we do that, maybe we make the code a little bit less flexible. Maybe it's less portable across scales, or it's less portable to different platforms, this sort of thing. With JAX, we're trying to let you hit any point on this Pareto frontier that you want, trading off these things. And to illustrate that, I want to give you two quick semi-technical stories about JAX doing this. So the first one's about sharding. Sharding is about how to take your transformer model and throw a bunch of chips at it to make it run faster or cheaper, this sort of thing. So how do we throw chips at a transformer? So here is a like prototypical transformer block for a dense transformer. This is like, I think, a Llama 3 block. I'm just going to look at, because it's simpler to illustrate, this MLP block. And I'm even going to distill a little more. I'm going to remove the like gating einsums there. And so here's our distilled example. The rectangles are arrays. The arrows are sort of data flow, and those blue X's are matrix multiplications. And the question is, how do we shard this thing? How do we throw chips at it to make it run faster? So maybe you ask, maybe you have an engineer, and hey, this engineer did a lot of work on pre-training or something. Skipped ahead. So when I talk about sharding, I mean, I want to distribute the data and the computation over multiple chips, like over many GPUs. And so let's say our parameters are too big to leave all held on all the chips all the time. So we're not going to replicate the parameters across chips. We're instead going to chop them up and save each piece on a different subset of chips. So the way I'm going to represent that is I'm going to take these parameter arrays and draw their pieces in these different shades of orange. That means that they're backed by data on different processors. When I say different processors, I'm going to imagine that all the chips you have, here there's just 4, we're going to imagine them in what I call a mesh. A device mesh is like an ND array of are devices. In this case, it's just a one-dimensional array of devices. And, we've named this axis that we've organized them on, this axis X. And so I'm going to write here, this is like we're sharding this array on its second axis over this X axis of the mesh. And here we're sharding on the first axis. Okay, more technical than other talks. Okay, so your first engineer, maybe you worked on pre-training. He's like, I know what to do. We should do FSDP. We should shard over the batch/sequence axis just like this. Shard these like intermediate activations. And the way these mapmels are going to work, we're going to like all gather the right-hand side, the parameters right before. It's going to be great. It's going to scale super well. And then someone else, another engineer says, this guy doesn't know what he's talking about. I've been thinking about, low latency decoding, and what we really need is tensor parallelism. We don't have time to like move the parameter matrices around. They're too big. Let's do tensor parallelism. And here's how that's going to look, how we shard things, and it'll, amount to this all reduced collective at the end. And then a third engineer is Dora the Explorer, and she says, "Por qué no los dos?" Let's do a mix of the two, and let's have like a 2D device mesh and do some FSDP and some like tensor parallelism or something. So what do? JAX is about giving you options. One option is shut up, I don't care, let the compiler figure it out. So I'm not even going to specify how these intermediates are sharded, and here's how you would write that code. It looks actually just like that, code on the first slide. You're just writing sort of regular NumPy as if you were programming just to your local computer, and the compiler is going to automatically decide how to shard all that data. It's going to automatically partition the compute, inserting the collectives, and scheduling them, etc. So this is the sort of like auto mode that you can use with sharding. So it's a sort of global view. You're not writing per device communication, but you're just leaving things up to the compiler. I think actually what's more interesting these days is having programs that are explicit about how you do shardings. And the way we surface that in JAX is we actually put the sharding into the type system, so it's sort of available to you. If you write, if you ever write code that's ambiguous about how it should be sharded, JAX will give you a trace time error. You can get these sort of ahead of time, and it'll say, hey, make sure you write an out sharding here to clarify exactly how this should be sharded. So here's a few examples of how those look for those examples we looked at. And there's a third option, which is where you really take more detailed control. And you say, no, I don't, not only do I want to specify the sharding, but I even want to take control of the collective communications for numerical purposes or to make sure it's overlapping exactly the right way. So with JAX, you can use all of these modes. In fact, you can compose them. You don't just like switch between them. You can actually switch between them mesh axis by mesh axis. So in some part of your code, you can say, I want to, let the compiler handle everything. In other parts, you can say, I'm going to write the collectives and handle all the details myself. All this stuff is important if you're going to, experiment with sharding strategies and get the most performance out of your hardware. If you're interested in this stuff, we have a tutorial book, this like scaling book online about how to scale models. It goes into much more gory detail than I did. What's very nice about it is it's a pedagogical resource that talks about sharding these transformer computations, and it happens to use the same it uses a mathematical notation that corresponds directly to the sort of JAX notation used in those sharding types that I showed. There's even code examples in this other repository for like Llama and DeepSeek, etc. Also sharing the same notation. So let me tell you a brief second story about kernels. What if you want to take even more control and really say, actually, I want to figure out exactly how each chip is tiling up my inputs and outputs, and I want to control when the memory accesses are happening so I can pipeline everything myself. How do you do that? So JAX has a kernel language built in called Pallas. You can write kernels for TPUs or GPUs using this language. And just recently, my teammate, Adam Pashka, tweeted out a tutorial we made on doing Blackwell mapmels in 150 lines using this. So this is the tutorial. It goes through, all the nice details about how to make the most of your NVIDIA hardware. Here's the kernel. Let's go through it line by line, starting at the top. Just kidding. We don't have time for that. But it does fit on a slide. This is actually, I copied and pasted the kernel from his tutorial, which is pretty fun. And interestingly, someone asked Adam, do you have something like that for TPU? That's a Matmel kernel on GPU. How do you do this on TPU? And he said, it sounds like a joke, but actually just the 5-line example gets you SOTA performance on TPUs. It turns out if you build a chip that just, is really good at matrix multiplies, it's good to, it's easy to make them do fast matrix multiplies. you can do distributed compute in the kernel as well. So that's it. That's all that I have. I guess if you have a takeaway message about JAX, it might be that it's useful to think in JAX terms. Like I think the JAX abstractions are good for thinking in terms of even if you never use it. If you want to learn about kernels or sharding, JAX is a good thing to know about. So that's it. Thanks very much.